So once again welcome back. In the last lecture we discussed in detail about precision and linearity. So what is precision? It is nothing but the ability of an instrument to read a number continuously from a given set of record at the time of measurement process. And what is linearity? It is nothing but the ability of an instrument via which we are in a position to define how linearly the output of that instrument follow the corresponding input. So in this lecture we are going to discuss some more operating parameters related to the static characteristics of a given instrument, and the first topic which we are going to cover in this lecture is sensitivity, and second topic is loading effect or you can say loading error. Now what is sensitivity? Sensitivity is nothing but the ability of an instrument to indicate the smallest change in the input and replicate that change faithfully as an output without any error. So that ability of an instrument is nothing but what? Sensitivity. So what is sensitivity? It is nothing but the ability of an instrument to indicate smallest change in the input and replicate that change faithfully as an output without any error. So that ability is nothing but what? Sensitivity. Now, in order to understand this particular phenomena in detailed manner, let us consider an example in which we are trying to measure a circuit current with the help of an ammeter, and initially we found that the value of circuit current is indicated by symbol I1 and its magnitude is say 2 ampere. And in the last lecture I told you that if you consider any electrical instrument, input to that electrical instrument is a current and output of that instrument is either a force or you can say deflection theta. In this case, let us consider that the output is say theta 1, which is going to be say 30 degree. So when the circuit current is 2 ampere, that ammeter indicate output as 30 degree deflection. Now due to some reason, let us consider that the circuit current is increased by a very small magnitude and the new value of circuit current is say 2.1 ampere. Now if you calculate change in current, which is nothing but delta I, so this is going to be equals to I2 minus I1, which is going to be 2.1 minus 2, that is 0.1 ampere. So 0.1 ampere indicate what? Change in the magnitude of current. Now if that ammeter is sensitive, then in this particular case the deflection or you can say the output of that ammeter may increase by a very small magnitude. Let us consider that in this case that ammeter indicate an output as say 31 degree, or it may possible that it indicate an output as 31.5 degree depending upon its sensitivity. So this difference of 1 degree or 1.5 degree indicate output corresponding to this smallest change in the input, which is nothing but sensitivity of that particular ammeter. Now if the ammeter is not sensitive enough, so even though the quantity or even though the magnitude of input current is changed by 0.1 ampere, still in that case also if ammeter indicate deflection of 30 degree, we can say that that ammeter is not sensitive in nature, or that ammeter is not in a position to indicate this 0.1 ampere of magnitude change, and we can say that it is not sensitive in what we can say nature. So this is what about the concept of sensitivity. Now mathematically sensitivity is indicated by symbol capital S, and it is defined as the ratio of output to the corresponding change in the input quantity. So this is the exact definition of what? Sensitivity. Now the mathematical formula to calculate sensitivity is different for different instrument. For example, in case of voltmeter, the mathematical formula to calculate sensitivity is given by sensitivity for voltmeter indicated by symbol say S suffix V is defined as the ratio of internal resistance of voltmeter divided by the full scale value, or you can say full scale voltage corresponding to that particular voltmeter. So this is the formula to calculate the value of sensitivity in case of voltmeter. Now what is the meaning of this? For example, let us consider that we are having a voltmeter of range say 0 to 100 volt. So in this case, this 100 indicate the full scale value or full scale deflection of that voltmeter, and let us consider that the internal resistance of that voltmeter is say 1000 ohm. So in this case, the sensitivity of this voltmeter is given by the ratio of internal resistance of voltmeter divided by its corresponding full scale value, or you can say full scale deflection. So I can write here as 1000 divided by full scale value, in this case is 100. So finally we will get output as 10, and the unit is, because it is the ratio of resistance and voltage, it is ohm per volt. So in this case the sensitivity of this voltmeter is found to be 10 ohm per volt. So this is how we can calculate the sensitivity of a voltmeter whose range is known to us and whose internal resistance is known to us. In the same way, we can also calculate the sensitivity of an ammeter. For example, we know the sensitivity to calculate in case of voltmeter is Rin divided by V full scale value, or you can say full scale deflection. Now suppose if you divide numerator and denominator of this equation by Rin, so I can write here Rin divided by Rin whole divided by V full scale value divided by Rin. Now this Rin will get cancelled. Here we are having 1. Now V full scale value divided by Rin. Now this V full scale value divided by Rin, ultimately it is nothing but the ratio of voltage and resistance, and V by R is nothing but what? I. That I is corresponding to full scale value. So I can write here as 1 divided by IFSV, which is nothing but full scale value. So this is the formula to calculate sensitivity in case of an ammeter. So formula to calculate sensitivity in case of voltmeter is nothing but the ratio of internal resistance of voltmeter corresponding to its full scale value or full scale deflection, and the formula to calculate sensitivity in case of ammeter is 1 upon its full scale value or full scale deflection of that particular ammeter. So this is what about the sensitivity. Now let us discuss the concept of loading effect and loading error. So what is this loading effect or loading error? Now what is loading error? It is defined as the error which is produced by a measurement instrument corresponding to its internal resistance value, or whatever the error which is introduced by the internal resistance of a given instrument at the time of measurement process, that error is defined by loading error or loading effect. Now in order to understand this particular phenomena in more detailed manner, let us consider an example in which we are trying to measure a voltage across a resistor as shown over here. Here I am considering a voltage source of say value 10 volt, and to this I have connected two resistors R1 and R2. Now let us consider that both the resistors are of same value, say 50 ohm, and here again say 50 ohm. Now our objective is to calculate the voltage across this resistor R2 with the help of some voltmeter. Now first of all we will calculate the actual value across this resistor R2 by analytical process. So how to calculate that? Because we know that these two resistors are connected in series, and to this series combination we applied 10 volt as an input. So if you apply voltage division formula, we can write voltage across resistor R2 indicated by symbol V2 is nothing but total voltage 10 multiplied by same by sum. So it is going to be R2 divided by R1 plus R2. So in this case it is going to be 10 multiplied by 50 whole divided by 50 plus 50. So the answer is going to be what? 5 volt. That means the actual voltage across R2 ohm resistor, whose value is 50 ohm, is nothing but 5 volt. That means when we connect a voltmeter across this resistor R2, this voltmeter has to indicate how much magnitude of voltage? 5 volt it has to indicate. Now let us try the case and identify how much amount of voltage is measured by this particular voltmeter. Now we know that our value of voltage which we need to measure with the help of this voltmeter is 5 volt. That's why we are selecting a voltmeter whose range is from 0 to 10 volt, because our unknown quantity is of 5 volt. That's why we have selected this range of 0 to 10 volt. And let us consider that the sensitivity of this voltmeter is say 5 ohm per volt. So what we have considered, we have selected a voltmeter whose operating range is 0 to 10 volt and its corresponding sensitivity is 5 ohm per volt. Now let us try to calculate how much this voltmeter reads a voltage. And to calculate that, first of all, what we need to do? We need to calculate the internal resistance of this voltmeter. So I can write here as internal resistance of this voltmeter. Let us consider that it is indicated by symbol small r suffix in. So R in indicate the internal resistance of this voltmeter. Now from the definition of sensitivity, we can write sensitivity is nothing but the ratio of internal resistance of voltmeter divided by its corresponding full scale value. So I can write here internal resistance of voltmeter is nothing but sensitivity of voltmeter multiplied by its full scale voltage value. So in our case, sensitivity of voltmeter is 5 multiplied by full scale value of this voltmeter is how much? 10. So the internal resistance of this voltmeter is going to be what? 50 ohm. Now this 50 ohm indicate the internal resistance of this voltmeter. Now when we connect this voltmeter of internal resistance 50 ohm across this 50 ohm resistor, so what this voltmeter is going to read? This voltmeter will read a voltage across a parallel combination of this R2 and its corresponding internal resistance. That means when we connect a voltmeter across this particular resistor of value 50 ohm, the circuit is now going to be like this. So this is going to be our 50 ohm R2 resistor, and across it there will be another resistance which is nothing but Rin, or in our case this Rin indicate the internal resistance of this voltmeter whose value is going to be what? 50 ohm. Now a voltmeter will read a voltage across this parallel combination instead of reading a voltage across this 50 ohm. So what we need to do? First of all, we need to calculate the effective resistance of this parallel combination. So let us consider the effective resistance is indicated by R actual, which is nothing but a parallel combination of R2 and Rin. So if you calculate this, we will get R actual is nothing but R2 in parallel with Rin. Two resistors are in parallel. Formula is product by sum. So I can write here R2 into Rin whole divided by R2 plus Rin. So it is going to be 50 into 50 divided by 50 plus 50, which is nothing but 100. So finally we will get R actual as 25 ohm. That means now the voltmeter will read the voltage across 25 ohm resistor. instead of 50 ohm resistor. Now let us calculate what will be the voltage indicated by a voltmeter. So Vm, which is nothing but a voltage measured by a voltmeter, in this case is going to be, supply voltage is nothing but what, 10 multiplied by actual value of this resistance seen by the voltmeter is nothing but R actual divided by R actual plus this R1. So it is going to be 10 multiplied by 25 whole divided by 25 plus 50. So it is going to be around 3.33 volt. So this 3.33 volt indicate the voltage measured by voltmeter. Actually, this voltmeter has to read how much amount of voltage? 5 volt, but it is indicating how much? 3.33. Why it is indicating 3.33? Because of its internal resistance of value 50 ohm. So this error is called as loading error, or you can say loading effect. So in this case I can write here as loading error is nothing but the difference between measured value and actual value. So measured value is 3.33 minus actual value is 5. So whatever the difference we will get, this difference is nothing but what? Loading error in this case. So this is what the importance of loading effect and loading error. So I can say that this loading error is introduced by this voltmeter because of its internal resistance. That is the reason I told you that what is loading error? It is nothing but the error which is developed or introduced by a given instrument because of its internal resistance, and this error is called as loading error. Now in order to overcome this particular error, what we need to do? We need to increase the magnitude of this internal resistance. Now let us consider another case. Suppose we have selected a voltmeter of same range, that is 0 to 10 volt, but now in this case the sensitivity of voltmeter is increased by a value, say 50 ohm per volt. Instead of having 5 ohm per volt, we are now selecting a voltmeter of sensitivity, say 50 ohm per volt. Now let us try to calculate in this case how much amount of voltage is indicated or read by this voltmeter. Rest of the thing is as it is. That means the circuit will remain same. So here I will draw the same circuit, 10 volt input, then here we are having R1 and here we are having R2. So R1 is 50 and R2 is again going to be what? 50. Now in this case, first of all, we are going to calculate what? Internal resistance of this voltmeter. So I can write here the internal resistance of this voltmeter is nothing but sensitivity of voltmeter multiplied by V full scale value. So internal resistance is nothing but sensitivity is 50 multiplied by full scale value, in this case is 10. Now the internal resistance of this voltmeter is going to be what? 500 ohm, which is previously 50 ohm. Now in this case, as we found that the internal resistance of this voltmeter is 500 ohm, now what will happen? This voltmeter is going to read the voltage across the effective parallel combination of this 50 ohm and this 500 ohm internal resistance. Now the circuit is something like this. So here we are having R2 of 50 ohm value. In parallel with this, we are having an internal resistance of value 500 ohm. Now R actual in this case is going to be what? R2 in parallel with R in. So what is R2? It is 50 in parallel with R in, which is nothing but 500. So directly we can apply the mathematical formula, that is product by sum. So it is going to be around this product by sum. Now if you calculate the value of internal resistance, in this case it is found to be around 45.45 ohm. Now in this case, as the actual value of, or you can say the effective value of this parallel combination of these two resistors is 45.45 ohm. Now this voltmeter is going to read the voltage across this resistor instead of this R2. So let us try to calculate the voltage measured by this voltmeter. So it is going to be the total voltage 10 multiplied by sum. So same is R actual divided by R actual plus R1. So it is 10 multiplied by R actual is 45.45 whole divided by 45.45 plus R1, which is nothing but 50. So if you calculate the voltage measured by this voltmeter, in this case the value is going to be 4.76 volt. But the actual voltage, or you can say true value of voltage, is nothing but 5 volt. That means we are moving towards our actual value. So this is possible only when the internal resistance of voltmeter is increased. Previously, when the internal resistance of voltmeter is 50 ohm, the voltmeter indicates the value as 3.33 volt. Now in this case, when the internal resistance of the voltmeter is increased and it is 500 ohm, now in this case the voltmeter is indicating a value of 4.76 volt. That means we are moving towards our actual value. So this is the importance of internal resistance of voltmeter during the measurement process, and this effect is called as loading effect. That is the reason ideally we can say that if we want to make this 4.7 exactly equals to 5 volt, what we need to do? We need to make the internal resistance of a voltmeter as high as possible. Ideally it should be infinite and practically as high as possible. That is the reason normally if you see the internal resistance of a voltmeter, it is very high, maybe say 1000 kilo ohm, or maybe it is defined in terms of mega ohm. That is the reason if you see the internal resistance of a voltmeter, it is very high. Ideally it should be infinite and practically as high as possible. So this is what about the concept of loading effect and the concept of loading error. In the next lecture we will discuss the remaining operating parameters related to the static characteristics of the instrument. Thank you.